All right, so we're going to be on StatKey today, like I mentioned. Let's just review what I'm going to be looking at here on StatKey. It's the middle column here, bootstrap confidence intervals. All right, and I'm going to do examples of all the four of these first ones here. Confidence intervals for means, for proportions, for a difference in means and difference in proportions, to show you what it looks like, how to interpret them, and basically the quiz that we'll have on Thursday will be 4 to the 5 questions will be StatKey graphs. You'll open them up on your quiz. Make sure you're using a computer. All right, no laptops, no iPads, no iPhones. Use a computer, right? And you should be doing it from now on for your quizzes, the remaining 2 quizzes for the test and for the final exam. You should not be using any other devices. All right, it's very important that you use a computer. If you don't have one, again, find one that somebody, borrow one, whatever you have to do. But you definitely need a computer for the rest of this course. All right, or a laptop. Okay.
So, Professor, we're we're taking a quiz, and you're saying I have only one computer, so I'm taking my quiz on my computer.
That's fine. I'm just saying you should take your quiz on a computer, not on an iPad or a
Oh,
phone.
that's what you're saying. Okay.
Yeah. Yeah, one computer is good enough. It should be on a computer from now on, not on some other device. So I know some people have been on other devices, and it's not going to work with StatKey. All right, StatKey, I don't think will open up. You have to. I have a. I should show this to you towards the end of the period. But I have a sort of a sample quiz. It's not a real quiz, but it's a sample quiz, which I'll provide to you. I'll post it where the regular quiz is on Thursday, and I have a sample StatKey graph in there that you just open up and make sure that you can open up successfully on your computer. All right, so you just go into the sample quiz and just take it like you're taking a regular quiz, except the only difference is it's not a quiz. You're just testing to see if the StatKey graph actually opens up for the question, right? And if it does, then you'll be fine for the quiz. All right, because I know last semester there's a couple people had issues with it and they had to reboot the computer and all that sort of thing. All right, so let's, before we actually create the StatKey graph, to the textbook that I'm using for the StatKey. This is the one up here, Statistics Unlocking the Power of Data. Obviously, you don't have this, but I'm going to display it to you for this today. And it has examples in here in the book itself, which you can see in the StatKey software. So I'm going to stop sharing this and go into the book. I think I have the book available. Right here. All right. This. Just get this out of the way here. Just a little bit smaller. All right, that's it. All right. All right, so once again, what is a confidence interval? Confidence interval is a range of values which estimates from sample data that estimates the population value. For example, if we want to estimate a population mean, we would take our sample mean and create a range of values around that mean. And we would say something like, with 95% confidence, I think that the population mean is inside that interval. That's the whole idea of what a confidence interval is. And I'm going to talk about the proper interpretation of a confidence interval also. There's a couple of PDF documents that I posted, which goes over the incorrect way of interpreting it. And there's only one way of interpreting it, all right? So on the final exam, typically the math department likes to ask a question about proper interpretation of confidence intervals. So you need to study this, the PDF documents that I'm going to show you on the proper interpretation. Anyway, two types of confidence intervals that they're talking about here. One is for proportions. Remember what a proportion is. Proportion is counting the number of people who answer a question a certain way divided by the number of people that we ask. That's a proportion, like a percentage. So when I say 0.275, I mean, when it says proportion of US adults with a college degree is 0.275, it means 27.5% of US adults have a college degree. All right, that's what it means. That's it. So what is a sampling distribution? Well, if we could think of all possible samples of, say, a certain size, maybe does this give you a yes? So n is 200 here. See 200. So suppose the sample size is 200. So suppose that everybody in this class plus other students take samples of 200 from the randomly select 200 people from all US adults in the population and ask them, do you have a college degree or higher? And if they answer yes, then you count them. And if they answer no, you don't count them. All right. And so picture having 1,000 samples of size 200. Okay, 1,000 samples of size 200. And each of these samples of size 200, you're asking people that question. So you can picture every sample is going to have a different answer, right? Because you're going to, everybody who does this sample, does the sampling procedure, is going to have a different group of 200 people. So you're going to end up with different answers to this question, a different number of people out of the 200 who say yes to this question. So the proportions are all going to be different. That's called sampling variability. So what we could do is we could use StatKey to do what's called simulation, and we simulate 1,000 samples of size 200. Okay, and and then we come up with a confidence interval, and I'll show you how to do that. So we're actually going to use this example right here, all right? And we're going to do a single proportion confidence interval. All right, so 0.275 is our we're going to 0.275 is our population portion. Let's assume that we do a random sample, all right, one random sample. And let's say instead of 0.275, we get 0.283. All right, I'm just going to make that up. Or actually, maybe just 0.28. We take a random sample 200, and we get 28% of the 200 who say, yes, I have a college degree. All right, so 0.275 is the population parameter. Now we're going to do a sample statistic. All right, so let's go into StatKey. CI stands for confidence interval, single proportion, that's what we want. All right. Can you see this okay? Yes? Everybody see this?
Yes.
All right, good. All right, now with proportions, I'm going to actually create the data myself here. All right. Now suppose we do 200 people. We ask the question, and 28%. Now 28% of 200, we just simply multiply 200 times 0.28. I hope all of you know how to do all that, what I'm saying to you. This is just basic arithmetic. You do it every day in life. So if I said 28% of 200, you know, you multiply 0.28 times 200. So 200 times 0.28, you can follow along with your calculator. 56 people. So 56 is the count. 200 is your sample size, all right? And that should come out to 28%. If we click OK, you can see on the right side here, you can see 56 is your count, 200 is your sample, and sample size, and there's your proportion. All right, everybody clear on that? Because that's really, you got to be really clear on what I just did. All right, it's basic arithmetic here we're doing. This is not algebra. This is, all right, so I just want to make sure that you're all comfortable with what I just did. Now, what StatKey does to create a sampling distribution, all right, instead of taking 1,000 samples, all right, and rerunning this process over and over again, simple random samples of 200, what we're going to do is what's called resampling. It's something that the people who created this program came up with. And what resampling means is, now you know that if you did a survey of 200 people and asked them each of the 200 whether you had a college degree or not, you know that a person's going to be asked once and that would be the end of it. All right. But suppose we took 200 people, we came up with their answers, and suppose we do with what's called sampling with replacement. All right, and what that means is once one person is sampled, we put them right back into the pool of possible people to be chosen again, and they can be chosen a second time or even a third time. All right, every time we want to choose somebody randomly from the population, this person could be chosen again. So when you have that ability to do that, all right, and this is not something we do in real life, but we're doing it for the computer. The computer's going to be doing this. We create what's called a bootstrap sample. And we're going to end up with a different count other than 56, because it's possible that some of the people said yes might be counted more than once, and some of the people who said no won't be counted at all. All right, if we use this sampling with replacement. So I'll just show you. Let's do one sample here, and notice now the count is 66 out of 200, and that's because some of the people said yes are counted more than once, and some people said no, counted less than once. So in this case, for this bootstrap sample, 66 divided by 200 is 0.33. There's your sample proportion. So basically what we're doing is we're repeating this bootstrap sampling process over and over again. And with StatKey, you just use these buttons here to give you the number that you want, the number of bootstrap samples. So I just click one for one of them. Now I'm going to reset the plot. I'm going to erase that, and I'm going to create 1,000 of them. There they are. There's 1,000 of them. By the way, the 55 here represents the last one it created here. But if I just move my cursor around in the main part of the plot, each of these dots represents a bootstrap sample. And there's 1,000 dots here, 1,000 of them. You can tell because it says samples is equal to 1,000. How do I know it's 1,000? Because I click this button up here, created 1,000 of these dots. So each of these dots represents a sample of size 200. And so I've created a sampling distribution. These are 1,000 samples of size 200. Each one of them can have a different count. All right. Many of them will have the same count. Like this is a dot plot. So every dot column of dots here represents the same count. So there are so many, there's quite a few that have 56. That's the largest one. Then we have 53 over here for the count, and then we have 60 over here. All right, and then there's one all the way over here that has 80. So there's actually one that of these bootstrap samples that had 80 people who said yes. And then we had, go all the way down here, we have a couple of them that said there's 36 of them, 200 said yes. All right, now each of them has a proportion, sample proportion, which is simply the count divided by the sample size. Now, if I want to create a confidence interval, that's what I'm going to do. First of all, I'm going to click the two-tail button here. And this computer program defaults to a 95% confidence interval. So what are you looking at here? You're looking at the middle part of this distribution is the 95% of all these dots. So 0.95, 95%, 0.95 of 1,000 is 950. So there's 950 black dots here that are inside this interval. And that means there are 50 red dots outside the interval. So there's 1,000 samples, bootstrap samples. This is a 95% confidence interval. And it multiplies to count the number of black dots here inside the interval. It simply multiplies 0.95 times 1,000. So there's 950 black dots. All right, it's done automatically for you. You just have to understand what this program is doing. That's all you have to do. There's no math involved with it. It's just logic. It's logic here. 95% of 1,000 is 950. There's 950 black dots. And the rest of the dots, the 50, are red dots. All right. Now, what's the 0.22 represent? That's the sample proportion. That's the smallest sample proportion for the black dots. All right. So this is the confidence interval, the interval of values. And 0.34 is the largest value, largest sample proportion that has black dots. All right. So this is what's called a 95% confidence interval. And the way to interpret this is the following. We're going to say with 95% confidence, all right, we believe that the true population proportion is somewhere in between 0.22 and 0.34. Now, what does 95% confidence mean? In general, it means that if we ran this sampling process over and over and over again, okay, we believe that each of those we believe that every confidence interval that we can create from an original sample, in this case, the original sample has 0.28. We believe that every confidence interval either has or does not contain the true population proportion. And the 95% says that we believe 95% of all possible confidence intervals will contain them and 5% won't. So in this particular case, this is our confidence interval for this sample proportion of 0.28. This is the confidence interval. Okay. And we believe with 95% confidence that the true population proportion, which I believe is 0.275, I believe in the problem. So it is in this case in this interval. But we don't know that in reality. We don't know the true population proportion. But we believe it's in this interval. All right. 95% confident. That means we're hoping that this is one of the 95% of the confidence intervals that contain the true population proportion. All right. So any questions about the correct interpretation of this? You sort of get what I'm referring to here. So we created a confidence interval built around this sample, the original sample proportion of 0.28. Right. The 0.28 is definitely going to be in the middle of this. All right. So, but we're building it around this using this bootstrapping procedure. The computer's doing all the work for you. The only thing you have to do is understand what you're looking at. These are, again, 1,000 samples of size 200. And we believe that with 95% confidence that the true population proportion is in between these two values down here. Okay. Now, what if we wanted a different level of confidence? Suppose we want 90% confidence. Well, we go in the middle box up here and click and just type in 0.90 for 90% confidence. Click OK. And now we have a different confidence interval. Notice this time 90% of the dots are black. That means 900 of them, not 0.9 times 1,000 is 900. That means 100 of them are red dots. And again, the confidence interval goes from the lowest black dot to the largest black dot, in this case 0.225 sample proportion up to 0.330 sample proportion. And that's our confidence interval for 90% confidence. Notice what happens is as the confidence level goes down, okay, the interval becomes more narrow. Notice that? This is something I will test you on. You should know this. And again, you have StatKey on your computer. You can play with it. All right, learn these things. as you change this value to something lower, this confidence level, this middle number in here, the range from this number becomes narrower. All right, narrower. If I made this larger, if I made this 0.99 for 99% confidence interval, notice it becomes wider. It makes sense, doesn't it? Because there's more black dots here. 99% is 990 of these black dots. There's only 10 red dots, if you count them, right? There's 4 here and there's 6 over here. I believe 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4. Oh, there's one over here, 5. All right, so there's 10 red dots. All right, that's samples that are not in the interval. So level of confidence means we're 99% sure. It means something like if we ran this sampling process over and over again, we expect 99% of the samples to have confidence intervals that contain the true population proportion and 1% that would not. And we're hoping that this particular interval that we got, all right, does contain it. It's one of those 99% that does contain it. All right. So that is the proper interpretation of this. Now, what is the wrong interpretation? All right. What is the wrong interpretation of confidence intervals? Okay, so let's share the screen here. Yeah, let's see. All right. Something not quite right here, so hold on. I think I have it now. Just give me a second. Zoom can be very annoying because you have to click the thing for it to show up. All right, now this comes out of this textbook that I have here. You don't have access to it, but this is on one of their pages. And this is giving you the common misinterpretations of confidence interval. These are the mistakes. Now there are 3 listed here, and I have created another PDF. It says additional misinterpretation, which gives you a 4th. So there's actually 4 different wrong ways of interpreting a confidence interval. So here's the first incorrect way of interpreting it. For let's say a 95% confidence interval. It says a 95% confidence interval contains 95% of the data in the population. No, that's incorrect. The 95% has nothing to do with the amount of data. All right, it just says 95%. What a 95% confidence interval means that if we repeat the sampling process many, many times, 95% of the samples should contain the true population parameter and 5% won't. But it doesn't contain 95% of the data in the population. That's a common mistake. Number 2, it says I am 95% sure that the mean of a sample will fall within the 95% interval. Well, yeah, that's the way we create a confidence interval, is we use the mean of the sample. So we're 100% sure that's going to happen. No, that's not what it means. It means that we're 95% sure that the population mean falls within this confidence interval, not that the sample mean does. It's obvious the sample mean does. It's the way we create it. Misinterpretation 3. The probability that the population parameters in this particular interval is 0.95. No, it's not a probability. When we say 95% confidence, it is not a probability. So you got to remember this. If I put in your quizzes or tests, the interpretation is the probability that the population mean or population proportions in that interval is 0.95. You know that's wrong, all right? Because it's either in that the population parameter is either in the interval or it's not, all right? And there's no probability involved with that. And then the last, the 4th one, it's very important. This is one that typically you need to know for the final exam and also for the test. This is a 4th misinterpretation. Confidence interval cannot estimate a population parameter for a population that is bigger or different than the population from which the sample is drawn. I'll give you an example here. If we're measuring the heights of adults aged 20 to 29 in our sample, we cannot state that the confidence interval constructed from the sample mean of these heights applies to all adults of any age. No, it only applies to adults aged 20 to 29. So you have to know your sample. Another example, if we asked Rowan students, do you like your statistics professor? All right. And some of them are going to say yes, some of them are going to say no. All right. And we want to know the proportion of Rowan students who like their statistics professor. All right. We cannot apply that estimate to all college students. It's only to Rowan students that we're taking the sample from the population of Rowan students. So we cannot apply that to all students. So this is very important to remember, all right? That you can only estimate a population parameter using a confidence interval from the population from which the sample was drawn. It has to be from that sample, and you can't generalize, you cannot estimate it to any other group of people, all right? Just to that population that you're taking your sample from. Any questions about that? This is posted. All of this is posted, and you should look at it, and when you take your next test or even your quiz, well, actually the quiz, I don't know if when you need this. Yeah, I think you may need it. I think there might be a question in there where you might need these things. So you may want to print this out and have it next to you for the rest of the course, basically. These two PDFs, they are posted separately. All right, no questions? Let's see if there's another chat. No, this is chat. All right. So let me close that out. All right, so let's now go back to StatKey. All right, so basically, this is how the graphs are created in StatKey. And on your quiz on Thursday, plus your tests, if I'm going to ask you questions about one of these are called a bootstrap sampling distribution. That's the name of this thing, this whole thing here. I'm going to ask you a question about confidence intervals. I will have this, you will open it up, not in StatKey, but in Canvas. All right, I found a way to create one of these, create a picture file of it, and then post it into StatKey. All right, and it will just open right up when you take your quiz and take your test. All right, just opens up, and then you'll look at it and answer the questions regarding it. All right, so on the right here is the original sample. So the original sample, we're treating it as if it's a population, and then we're creating bootstrap samples from it. In this case, 1,000 of them. Now, by the way, I can create any number of bootstrap samples. If I want to create 2,534, I'll create 2,534. Yeah, I did it. There we go. I've now created 2,534 bootstrap samples, and then I'll click the two-tail thing here, and I've created a 95% confidence interval. And if I wanted, and then I can create any confidence level I want. So if I wanted an 85% confidence level, I just type in 0.85 in the middle here, middle number, click OK. Now I have an 85% confidence interval. All right. So this number in the middle is the level of confidence. Okay. This is down here, or to the left is your lower part of your confidence interval. This is your upper part of your confidence interval. So 0.235, lower limit of the confidence interval, 0.325, upper limit of the confidence interval. Up here's the number of samples. Okay. And it gives you the mean of all these 2,534 samples and the standard deviation of them. All of that's given to you. All right. Okay, now let's do another type of confidence interval for a sample mean. So the way to get back to the original screen is just hit the StatKey button, and I'm going to do It says confidence interval for single mean, median, or standard deviation. We're only going to be doing means in this course, by the way. And it defaults to a mean. Here you can see you have a choice. You could take one of those three, but I will never ask you anything about a median or standard deviation. We're good with that. And they do have, by the way, several examples here, example files, which are actually mentioned in the book. We create bootstrap samples with them. And so let's actually use this Mustang price. Mustang, this is a car. Hopefully you know that's an automobile. And these are prices of Mustangs, I guess, different ages of Mustang cars, all right? And then how many are there in this sample? There's 25 Mustang cars. Now the number here says 15.98 is the median, the mean for the original sample of 25 Mustang cars. Obviously, this is in thousands of dollars. So when it says 15.98, we multiply that by 1,000, and it's actually talking about a $15,980 Mustang, a used Mustang car. All right. So hopefully that's obvious to you. That's what it's referring to. It does give you the median and the standard deviation. Now, if I picked one of these bootstrap samples to derive from that, notice that I get this bootstrap sample. Notice that the mean now of the bootstrap sample is 17.48, and it gives you median standard deviation. Now, if I printed this out on the quiz, and I ask you some questions about what you're looking at, if I ask for something like, what is the standard deviation of the original sample, you would say 11.114. If I ask you the standard deviation of the bootstrap sample that you're looking at, it's 11.112. All right, so just read it right off of here. Just make sure you understand that this is the original sample, and this is just one bootstrap sample that's being shown. All right, and once again, if I wanted to create from this bootstrap sample, let's say I wanted to create 500 bootstrap samples, and I want to find the confidence interval, I will create 500. 1, 2, 3, 4, 5. And here is my bootstrap confidence. This is my bootstrap sampling distribution, all of these dots. And if I want a 95% confidence interval, didn't give that to me here, then I have to click this middle box and put 0.95 here. And there it is. All right. So I have 501 actually samples here because I generated that one to begin with. So it's 501. But 95% of those dots are the black dots here. They're the ones inside the interval, and the red dots are outside the interval. And here's the lower limit of the 95% confidence interval. It is 11.87. This is the sample mean. This sample mean, by the way, represents a car that costs $11,870. All right, remember this is in thousands of dollars. The upper level of the part of the interval is 20.942. This is a car that's worth $20,942. All right. And again, they gave you the original sample. This is the original sample up here. The bootstrap sample is shown down here is the very last one that I showed, but if you just move your cursor around on these dots here, whatever your cursor is over, it'll show you that bootstrap sample with the mean and the standard deviation, all of that. All right. Okay, so these are all 500. There's all 501 of these, and 95% of them are in here. So if you wanted to count the number of them, you just multiply 501 times 0.95, would give you the number of black dots, and the number of red dots would be the whatever's left over. So again, the way to interpret this is that say that 95% of all that we're 95% sure that the true population mean is somewhere in between 11.87 and 20.942. Right? Or if we wanted to be more precise, the true population mean price of a Mustang car is somewhere between $11,870, $20,942, and we're 95% sure that the true population average price of a Mustang car is somewhere in between those two values. Okay. Now, if we wanted to create a, let's just reset this. Let's say we wanted to create a sampling distribution with 2,000 samples. There's 2,000 right there. We wanted, and now we'll do our, let's say we wanted a 92% confidence interval. We'll just click the middle box here, click 0.92, enter. Now 92% of the 2,000, right? And I believe that is a 184, I'm sorry, 92% is not 184. What's 92% of 2,000? So it's 2,000 times 0.92. So that's 1,840 of those 2,000 dots are inside this interval. Right? How did I get that? 0.92 times 2,000. So there's 1,840 dots that are inside the interval, and there's 160 dots that are outside the interval. You don't have to count them, just use your calculator to come up with the arithmetic. Now, what does this interval say? I'm 92% sure or 92% confident that this particular interval between 12.202 and 20.078 contains the true population mean. All right, 92% confident. Notice I had 95% confident before, and we noticed that the interval was wider. All right, 92% means it's going to be narrower. All right, this is narrower than before. I mean, let's just check it out. Go back to 0.95 to make sure that's true. Yes, notice this is a wider interval. So the larger the level of confidence is, the wider the interval. And that makes sense because the number of black dots goes up when we increase the level of confidence. But if we, again, reduce it back to 0.92, we notice the interval becomes more narrow because there's fewer black dots in here. Okay? So now, it's very important to also remember that this confidence interval is only for this particular sample. All right, this particular sample that has a mean of 15.98. We created all these bootstrap samples from this original sample that has a mean of 15.98. If you and others did random samples of 25 Mustang cars, you will come up with a different mean because you would have different Mustang cars in your sample. You would have a different mean, and therefore you would have a different bootstrap confidence interval. The bootstrap confidence interval will change depending on which sample you have. All right. So these intervals are not the same for all samples. This interval I just came up with is only for this particular sample. And by the way, this is computer simulation, which means that if I ran this again for 2,000 samples, I get a different answer here again because the computer is doing this randomly, creating these bootstrap samples randomly. It'll come up with different bootstrap samples for the 2,000. So even running this again will create different numbers here, different confidence intervals. All right, so just know that for this particular confidence interval, this is the bootstrap sample. This is the bootstrap confidence interval. And if you did another sample or did many, many different other samples, you would get different confidence intervals. But a 92% confidence interval for this particular sample indicates that we're 92% sure that the true population mean is in between these two numbers. All right, that's it. Any questions about what I've done so far? So what I'm showing you is the types of questions that I'll be asking. All right, I may be asking you a question like, how many samples are there? All right, so I'll display this box right here. All right, in your quiz or in your test, I'll say how many samples there are. Well, just look on the upper right-hand corner. This number here is the number of samples that are down here. All the dots, all of them. If I ask you how many bootstrap samples there are in the interval, just take this number in the middle here and multiply it by the number of samples. That gives you the answer. If I want to ask you how many samples are outside that interval. Well, you take this number, multiply it by 2,000, and then subtract that product from 2,000. That gives you the remaining number. So 0.92 times 2,000 in this example is 1,840. 2,000 minus 1,840 is 160. There's 160 red dots outside the interval. Right? This is simple arithmetic. This is not advanced mathematics here, folks. Arithmetic. That's all it is. That's all I'm going to be asking, things like that. I'm going to ask you what's the confidence interval. Here it is, down here. I'm going to ask you the level of confidence. That's the number in the middle here. These two numbers are irrelevant. Forget about these two numbers. These don't matter. All right? They don't matter. All right? So, I mean, if you add these two numbers up and add this number in the middle up, you come out to 1, always. But you don't need to know these two numbers. I'm not going to ask you about these two numbers in a confidence interval question. I'm going to ask you about the number in the middle. I'm going to ask you about the confidence interval. I'm going to ask you the number of black dots, the number of red dots. I'm not going to call them black dots, by the way. We'll say how many bootstrap samples are inside the interval. Well, that's the number of black dots. I'm going to say what's the number of bootstrap samples outside the interval. It's the number of red dots. Okay. Again, I might ask you something about the original sample. What's the mean? What's the median? Standard deviation. Or if I print out a bootstrap sample, one of these bootstrap samples here, if I print them out, I can ask you the same questions. You just read it right off the chart here. Right? And then I ask you interpretation questions. Or I might give you a true-false question about interpretation. And remember, you know the 4 different types of misinterpretations now. So you look at it and say, is that one of the 4 types of misinterpretations, or is it the correct interpretation? That's the sort of true-false question I'll be asking. All right, let's go back to StatQ. There are 2 other types of confidence intervals that you're responsible for. Now the quiz, I looked at the quiz that I created. Does not have any confidence intervals for these 2 types, but you do need to know them for the next test and for the final exam. Right, but I'm not going to test you on these 2 here for this quiz coming Thursday. Let's look at the confidence interval for difference in proportions. Now, what does that mean? It means we're going to have 2 groups of people. Instead of having one group, and we're looking at a proportion just for one sample, we're going to have 2 samples, 2 groups. And we're going to count the same thing. All right. So here's an example here. I'm not totally sure what proportion of what we're counting here, but suppose we're asking, I know what this says. I know what this is. I believe this has to do with the use of the cell phone for checking emails or something like that, or text messages. I think it has to do with text messaging. Yes, using text messages. In this particular study, and this was a while ago, all right, they asked 800 teenagers and 2,252 adults, okay, to use text messaging, all right, as a primary way of communication instead of email, something like that. Right? So out of the 800 teenagers that were asked the question, 696 of them said yes. Out of the 2,252 adults, 1,621 of them said yes. All right. So we asked the same question to the 2 groups, and we want to know if there's a difference between teens and adults in terms of proportions. Now, not in terms of counts, because there's so many more adults that were asked this question. It's unfair to just say there's 1,621 adults and there's only 696 teens. You can't compare these 2 numbers because these are out of much different sample sizes here between the 2 groups. So it's better to do the proportions. So for the adults, 1,621 adults saying yes, divided by the 2,252 adults that were asked the question, is a proportion of 0.72. For the teens, 696 divided by 800 is 0.87. So obviously, many more teens were asked, were saying yes to this in terms of a proportion of the teens than adults, right? 87% of teens said yes in the sample, 72% of the adults said yes. So if we took the difference between these two, if we said teen minus adult, in other words, the teen proportion comes first, then the adult, then 0.87 minus 0.72 is 0.15. This means that 15% more teens, 15% more teens said yes than adults to this question. Okay? If we're looking strictly at percentages here. So, what is the bootstrap sample going to be? It's going to be a bootstrap sample of the difference between the proportions for teens and the proportions for adults. In this case, the sample, this number is the important number here, 0.15. That's the difference. We're looking at differences in proportions. Remember, p hat represents the sample proportion, and p hat 1 represents group 1. Group 1 in this case is teens, and group 2 is adults. So when I say p hat 1 minus p hat 2, I'm saying the difference in their proportions between teens and adults. And I'm going to create, let's create 2,000 of these. Each of these 2,000 bootstrap samples, these numbers down here represents the difference between teens and adults. All right? Difference in proportions between teens and adults. That's what it represents. So let's create this, make this 0.95 for a 95% confidence interval. All right. So how many bootstrap samples did I create? 2,000 of them. 95% of 2,000 gives me the number of bootstrap samples that are inside the interval. So that is 1,900. 2,000 times 0.95, there's 1,900 of these black dots. That means there's 100 red dots. So there's 100 bootstrap samples that were outside the interval, and there's 1,900 that are inside the interval. Okay, each of these dots represents a difference between the teen proportion and the adult proportion. For example, that the one that you see here, notice it says 0.176. That would be down here somewhere, 0.176. Actually, I changed it here. Sorry about that. But let me just keep my cursor on one of them. There, that one there. Notice it says 0.163 for the bootstrap sample there, for the difference in between teen and adult. Do you see that? Go to the right there, look at the bootstrap sample box. Go down to the row, it says teen minus adult. Go all the way to the right, under proportion, 0.163. That is the difference in proportions between teen and adults. That dot says, for that particular bootstrap sample, 16.3% of teens, 16.3% more of teens than adults use text messages out of those groups, right? So that's the percentage more of teens that use text messaging than adults for that particular sample. Now the sample includes all of these people. All right, if we added up 800 plus 2,252, there were 3,052 people in the sample. 800 of them were teens, 2,252 of them were adults. All right. Now, what does this confidence interval represent here? Say something like we're 95% confident that the true population difference between teens and adults, true population difference in proportions between teens and adults is between 0.12 and 0.181. We're 95% sure that the true population difference in proportions is between those two values. All right, or we could say that the true population difference in proportions is where the teens are 0.12 higher in proportions than adults, and 0.181 higher, teens that are higher than adults. All right. So these are the differences between teens and adults. So 12% higher for teens than adults, and 18.1% higher for teens versus adults. This is a difference in proportions. We're comparing two groups here, and we're saying that the true population difference of proportions is between 12% higher for teens and adults and 18.1% higher for teens and adults in terms of using text messaging. This is called difference in proportions. And again, if I wanted to change this to 90% confidence, notice the interval now becomes narrower because there's fewer black dots here. Now there's going to be 1,800 black dots and 200 red dots. Then if I wanted to change this to 0.99, the interval becomes wider because there's many more black dots. Now 99% black dots, and that's equal to, take 2,000 times 0.99, that's 1,980 black dots. That means there's 20 red dots. 1,980 of these samples are inside the interval, and 20 are outside the interval in this case. Okay. Any questions? Very silent. I don't know if you're understanding what I'm doing and not understanding, but I hope you are. All right, you can obviously listen to this video again. Let's go back to StatKey. We have one more type to look at, and that's the difference in means. Okay, so let me see if I can find, all right, this one actually looks like a good example. Suppose we ask two groups of people, males and females, how many hours a week do you exercise? Okay. And there are 20. Now, N1 represents, I believe, let me see, let me look at this thing. Check this out. Let me see. Hold on 1 second. Let me just check that bootstrap sample here. All right. Yeah. So suppose we have two groups, the males and females. We ask the question, how many hours a week do you exercise? Now, males are group number 1, and females are group number 2. That's the way to do it here. If they're going to show you the dot plots for each one of these groups, the one on the bottom is group 1, the one on the top is group 2. All right. So, for example, the original sample here, out of now group 1, there are 20 males. That means there's 20 dots here for the men. And N2 is 30, so there are 30 females. There's 30 dots for the females. All right. The average male, if you took all these the numbers here and averaged all 20 of the male responses, the average male said 12.4 hours, was 12.4 hours, the average of the 20 males. The average of 30 females is 9.4. There's M here and F there represent male and female. The difference between the two means, the two sample means, is 3. You can see up here, x1 bar minus x2 bar is equal to 3. That's 12.4 minus 9.4 is 3. Okay? And here's a bootstrap sample here. For this bootstrap sample, notice that the mean for males is now 12.35, and the mean for females is 9.467. If you subtract those two, the difference in their means is 2.88. So we wanted to see if males exercise more on average than females. That's really what we're looking at here. There's x1 bars representing the males, x2 bars representing the females. Okay. Now I'm going to create, let's say, let's create 830 of these bootstrap samples. So I'm going to create 800. I'm going to click this 8 times. Oops. Start again. 800 and 30. 1, 2. All right. There's 830 of these bootstrap samples. And I'm going to click the 2-tail again. Now this is a 95% confidence interval. Notice the middle button, it does show 0.95. There are 830 of these bootstrap samples in this bootstrap sampling distribution of sample means. This is for sample means now. Okay. The middle here shows it's a 95% confidence interval. And the bottom here on the left gives you a number. That's the lower part of the interval. The right is the upper part of the interval. Okay. The number of bootstrap samples that are inside the interval is 0.95 times 830. So we multiply 830 times 0.95. We get 747 black dots. 830 minus 747, or 737, gives you 93 red dots. Okay. Everybody clear on that? Now I came up with the number inside the interval and how many outside the interval. Again, 830 times 0.95 gives me the number of black dots, number of bootstrap samples inside the interval, and 830, and then take that number and subtract it from 830 gives me the number of red dots, the number of bootstrap samples outside the interval. Here is the confidence interval. Now notice that the left one is negative 1.287. Now remember, the difference between these two means is that the average, the first x1 bar is the average exercise weekly time for males, and the other x2 bars for females. So x1 bar minus x2 bar is the amount that males exercise more than females. If it's negative, it means that females are exercising more than males. Does that make sense? So a positive number means males are exercising more than females. A negative number means females are exercising more than males. So what this interval is saying is that we expect the true population difference in exercise averages between males and females to be between negative 1.287, which means that females are exercising on average 1.287 hours more than males, up to positive 7.758, which means males are exercising on average more than females by 7.758 hours. We're expecting the true population difference in means to be in between these two numbers. So it is possible that the true population mean is that females exercise more than males, but it would be on the left side here. More likely, it's going to be males exercising more than females. Again, if we wanted to change the confidence interval and we type in 0.90, we will have a narrower interval. Difference between these two numbers is more narrow. Because 90% of 830 there are fewer black dots now, more red dots. And then if we increase this to say 97%, I'm just making up some numbers here. Notice there are now more black dots, and therefore it's a wider interval than before. Okay. Any questions? All right. So as you could see today, there's very little math that you need to know for this, right? You have your calculator next to you. The only reason to use your calculator is to calculate the number of black dots, the number of values that are inside the interval, the number of red dots that are outside the interval, right? And that's it. That's the only reason you're going to be using your calculator. Everything else is just a matter of interpretation and know what these numbers mean. The only numbers that you need to know on this chart is the middle one. This is the confidence level. Okay. And these two numbers down here, this is the confidence interval. That's it. And then the interpretation. You have to know what the proper interpretation is versus what the improper interpretation is. And that's it. That's all you have to know. All right. Any questions? So really, the math department has made this easy for you in terms of the math. All right. There's no formulas in creating confidence intervals. And it just have to know how to use this. And actually, you don't even need to know how to use StatKey, but I'm showing you how to use it, and if you want to practice with it and try to understand what I'm doing, if you want to, let's say, run the video again and then practice using StatKey, you can open up StatKey and do what I'm doing here, and see, and just make sure that you understand, you know, everything I'm doing, all the steps. Okay. So that is it for confidence intervals. That's it. It's just, you need to know what a confidence interval is, that it's a way of estimating a population parameter. We use and then you do know that I showed you last session, that there are formulas that you can use with margin of error. If you remember last time, I talked about margin of error. You add and subtract the margin of error from the sample mean or sample proportion, and you get your confidence interval. That's the traditional way of doing it. And I'm showing you the alternative way. This is the way that the math department wants you to learn how to do it, so you don't have to use formulas. Okay? But again, you have to sort of know what this process sort of means, what we're doing here. All right. And as a review, one more time, we're taking a sample, and then we're creating bootstrap samples from it using what's called resampling. Right. Using what's called sampling with replacement. That means that the bootstrap samples will be different than the original samples. And then we create a bunch of them, like 1,000 of them, or in this case, 830 of them, using these buttons up here. Then we click the two-tail button here, and then we change the level of confidence here. We get different confidence intervals, and then we just need to know what the interpretation is. In this case, 97, we're 97% sure, 97% confident that the true population difference in means between males and females exercise times is between these two numbers. That's it. Any questions? All of you are fast asleep, hopefully. I guess if you have insomnia, this is the way to catch up on your sleep. But actually, you really need to pay attention to this video, because this is it. There's no reading other than what I'm showing you. All right, there's no reading in the textbook. The seeing
So
through
how do we
statistics
find the definitions for this stuff?
through the video. Listen to the video and take notes. All right, that's how you do it. Because again, if you had the textbook, this particular textbook that I was referring to, then it wouldn't be a problem. It's in the textbook. No, the textbook that they give you is not useful for this. All right, not at all. So therefore, watch the video again and follow the steps. And actually, you don't even have to create these, right? You just follow what I've done, what I'm saying, and interpret things the same way. And just know where everything is in the StatKey, where the level of confidence is, where everything is. And again, I've said it. How many times have I said it? You know, repeated myself many, many times. So you should be able to look through this video again and then follow along, and then you should be able to do the quiz and test successfully. Because again, you're not responsible for creating these. I'm not going to ask you to create one. Just asking you to look at one and tell me what you see.
And the quiz is just on the StatKey?
Yeah. Yeah. Okay, so just re-watch the video again, and you can always pause it, rewind it, whatever you want to do, and open up StatKey, play with it while you're watching. See if you can replicate what I'm doing. All right, because that will be helpful in remembering this. And you don't have to memorize it, right? It's just, you just take some notes. And do it in your own way. I mean, my notes, if I showed you stuff, it wouldn't be the way you would learn. So you can make your little drawings too, right? You can draw and say, all right, this button in the middle is for level of confidence. These two buttons are down here, and just make a little drawing on your piece of paper and have it next to you. Whatever way that is helpful for you to learn something. All right, everybody's different.
Okay,
But everything that, as far as the PDFs are concerned, for the, that's posted. That's also posted. All right, now, as far as, basic definitions, there's no basic definitions in this quiz, but if you want to know what a confidence interval and things like that, in 20.1, 20.2, and 21.1, I believe, those sections in your textbook, it gives you sort of a basic definition. But again, I'm not even posting anything from that book because there's stuff in there that is beyond this course. All right, I don't want you to learn the more advanced stuff because then it defeats the purpose of taking this course, right? You don't want to take the Stat 1 course. All right, so just watch the video again. That's what I would tell you to do. Watch it again. Watch it a third time if you want, but watch it again and just follow along, and you should be all right.
if I can't pull the videos up, I might have to email you because a couple times I tried to get the videos up. They don't come up. They don't.
Well, there's
That's
nothing I can do
I
about that.
you said I have to copy and paste. I forgot you said that. Okay.
Yeah. The videos are created on my computer. So I go to YouTube, create them there. They're YouTube videos, basically. So when I'm pasting onto the onto Canvas is the link to the YouTube video. So there shouldn't be any issues. You should be able to open it up. They're YouTube videos.
Yeah.
Every time I open it,
I've had to
I click it
copy
and it opens up.
paste.
Huh?
Yeah, it don't do that for me. I had to play around with it and
Right.
copy and paste. I saw your old videos from your last semester. That's what I can just hit and comes on. But
Right, they're still there too.
our classes, they
Yeah.
don't just pop up. I have to copy and paste to
Yeah,
get them on.
All right. Well, that's what you have to do. Of course you have. You take the link and you copy it and paste it into your browser. That's a
Okay.
whole. Well, that's
All right.
yeah.
If I have any issues,
There's no other
I'll
way of
just,
doing it. You have to.
yeah, I'll just email you if I have any issues.
All right. Okay. But I did
All
leave
right.
last semester's videos out there too, so they're the same thing. It's the same.
Yeah, I did. I looked at them. Okay.
All right. You can look at them
All right.
too if you want. Yeah. Okay, guys. Any other questions? All right. So stop the